This is a group theory. Consider J as A plus B root of 2 under the binary operation. By the way, yesterday we were looking at binary numbers. This has nothing to do with binary numbers. A binary operation are just two things operated together. It's usually something other than just add, subtract, multiply, divide. And here it's a complex, or it's not a complex, but it's a irrational number. Show that J is closed. So what we're going to do under multiplication, we're going to go A plus B square root of 2. Would you write that? Times C plus D square root of 2. And so when you multiply those out, you're going to get AC. You're going to get BC times the square root of 2. And you're going to get BC times the square root of 2 and AD times the square root of 2. And you're going to get BD times what? Times 2. Now what's interesting about this is that this part is real and this part, well, I'm going to rewrite it. AC plus 2BD, that's real. And then this part, BC plus CD times the square root of 2. This is going to be, actually they're both real. I should have said these are going to be integers. Because A and B are elements of the integers, this will be an integer and this will be an irrational. Why is it irrational? Root 2. But is this still of the form A plus B root of 2? If A and B and D are integers, this will stay an integer. B, C, and D are integers, that'll stay an integer. So this is therefore closed under binary multiplication. How about part B here? How about the identity? What can we multiply A plus B square root of 2 by to get itself? Yeah, it's going to be, the identity of this is going to be 1 times that. So we're going to say that identity under multiplication is just going to be equal to 1. Now, in order for that to be 1, what would A have to be and what would B have to be? What would B have to be in order to make this identity 1? It's not hard. B, what would B have to be? 0, because we want it to be 1. What would A have to be? 1. There you go. So this is what they're looking for. Yes, the identity of the whole thing is 1, but to get that, A has to be 1 and B has to be 0. Okay. 1 minus square root of 2 has an inverse. Did you go 1 minus square root of 2 times A inverse has to equal to the identity? What was the identity? 1. So A inverse is going to be 1 over 1 minus square root of 2. How many got that far? Awesome. Then what are you going to do? You're going to multiply top and bottom by what? 1 plus square root of 2. Perfect. And so this is going to be equal to 1 plus the square root of 2 over what? Yes, 1. Middle terms drop out, and you're going to get minus 2, which is negative 1, which is negative 1 minus root of 2. That's what A inverse is. Now, tell me, does that fit into the A plus B root of 2 format? Yes. So, therefore, inverse exists. Now look what happens when I do the same thing here. A inverse is 1 over 2 plus 4 root of 2. When I try that one out for size, 2 minus 4 root of 2, 2 minus 4 root of 2. That's going to give you 2 minus 4 root of 2, but in the bottom, you're going to get 2 times 2 is 4, minus 16 times 2, which is plus 34? No, 32. So I'm going to do this one more time here. 4 times 4 is negative 4 is negative 16. No, this is minus. I was thinking i's here. 4 minus 32. So this is going to be 2 over negative 28 minus 4 root of 2 over negative 28. And what do you think, Gavin? By the way, good video today. Negative 1 over 14 plus square root of 2 over 7. Why is this not an inverse? They're not integers. So if we match these up to a plus b square root of 2, you're going to get a is negative 1 over 14 and b is equal to 1 over 7. These are not elements of the integers. Therefore, inverse does not exist. I like that one. Let's move on over to D. Consider the set here. Show that the subset G of elements of J have inverses, forms a group of infinite order. So let's go through that list. Let's do associativity. Associativity, because why? Multiplication, yeah. Operation. The inverse exists. Inverse and identity exist. We showed that, didn't we? The identity was 1 and the inverse exists. And then one more thing we need to do here to show that it's a group. Am I missing something? Yeah. Oh, we also have to show that it's closed. Closed, and you can look at part A. We showed that. So associativity, inverse identity, closed, and then it says forms a group of infinite order. If multiplication works, will that power work? Is that what you can say? Since multiplication, what do you think? Multiplication, repeated, I would say repeated multiplication implies infinite order, therefore forms a group of infinite order. Consider this one was easy, but I need a little help on one little piece here. Find the inverse of a plus b square root of 2. So that's what we're going to do here of the general. So we said that the identity was what? What's the identity of this? 1. So A inverse is equal to 1 over A plus B square root of 2. So then A minus B square root of 2, A minus B square root of 2. And then when we simplify this, you're going to get a minus b square root of 2. Gavin, are you writing this down? Good. A squared, the middle terms drop out. It'll be minus b squared times what? 2. There you go. That's the inverse. So if we rewrote this A inverse, it's going to be a over a squared minus 2b squared minus b over a squared minus 2b squared square root of 2, right? And so in here it says, show that a squared minus 2b squared divides exactly into a and b. Haven't we kind of shown that here? Or not? We haven't? How would you show that? See, they didn't really, they said this answer implies that a squared minus 2b squared divides into it. That's what they said. Yeah. Implies that a squared minus 2b squared divides a and b. And in this part, in part 3, then what would a squared minus 2b squared have to be equal in order for this to be an integer, a or b? What would it have to be? Yeah, 1 or negative 1, because otherwise what would happen is it would require that, you know, this would be like both evens and divided by 2, which you can't count on. So if all that they said for these is that since you've got this relation here, an a over this, b over that, that's kind of implies that this is going to have to divide them. And the best way for that to happen is if we get 1 and negative 1. 2, it says an integer n is given in base r and expressed in base s. So you want base r, and it's in, you're going to use base s. In base 5 of an integer, in base 5 an integer is written 1031. Express it in base 10. So did you get 1 times 5 to the 0, 3 times 5 to the 1, and 1 times 5 to the third, because there's no 5 to the second. So this is 125 plus 15 plus 1. I get 141. Base 10. Anybody disagree with that? Is that what you got? And then given that n is 365, r is 10, s is 7, find the values of a0, a1, a2, and so on. So 365, and this is given in base 10, is going to be, all right, now we got to use your calculators here. 7 to the what power is closest to this without going over? I think 3 might be close. 7 times, or 3 times 10 to the 7, yep. 3 times 7 to the third. Is that right? Okay. What is 3 times 7 to the third? What is that? 1 7 to the third? Oh, okay. And what is that? 343. So 365. So this is just going to be 22, which is going to be how many 7 to the firsts? 22. 3. There's my 3. And then this is going to be what? How many left? 1 times 7 to the 0. Now we got to go back in this form. The form is A0, A1S, A2S squared, and so on. So I'm going to list A0, A1, A2, A3. Careful here. A0 is 1. A1 is 3. What's A2? Thank you. And this one is 1. And that's correct. I think you should be fine with C. It's the same kind of thing. I'm not going to do it. Nothing new really there. There is a little something new. Let's do it anyway. This one here is 899 base 10 is going to be 12. How many 12 squareds is that going to be? 144 times what is closest without going over? 6? Try it. So what's 6 times 144? Real quick. 864. Now I'm good from here. 5, 3, 35. That's going to be how many 12s to the firsts? 2. So that's 24. And so then it's going to be 11 left. Plus 11 times 12 to the 0. So this is going to be A0 is how much? Yeah, and how do we write 11? A is 10, B is 11.
Is this standard internationally or?
Correct. I don't think so. So A1 is 2, A2 is 6. So it says, hence, write down the integer in base 12, which is equivalent to 899, and it is 620b.
Why would you create new symbols that don't have to learn instead of just using ones that everyone knows?
Because then it's confusing. Nobody knows.
Someone puts a TP on it. Maxwell spell
Okay, but
All right, last one. Show that 121 is always a square number in any base greater than 2. Oh, it's not bad. It's not too bad. So 121 is going to be, okay, in any base, you're going to have, I don't know what it's going to be, so let's call this a ratio or a base R. 1 times base R to the second, 2 times base R to the first, and 1 times base R to the 0. We don't know. We're just going to call it a base. So you're going to go 121 is equal to R squared plus 2R plus 1. Now what? Yeah, it's going to be what? RR 1, 1. What is that? That's R plus 1 squared, yep. Therefore, 121 can always be written as a square R plus 1.